Dr. Gregory Fahy, who everybody here knows. The Executive Director and Chief Scientific Officer of 21st Century Medicine, from whom, of course, we license our cryoprotecting solution. Thank you for that. A biotechnology company devoted primarily to complex system cryopreservation. Greg is a fellow of and the new president of the Society for Cryobiology. Can you believe that?
Well, good morning, everybody. It's great to be here. Thank you, Max, for the introduction. And wasn't that a fantastic presentation by Dr. George Church? George is a tough act to follow, but I'll do my best here. So I'm going to touch on a subject that's important to me as a cryobiologist and ultimately has significance for how cryonics is viewed by non-cryonicists, and that's the concept of falsifiability and how that relates to science. We're going to discuss that topic by relating it to an experiment that was done a few years ago and is still actually ongoing, involving the examination of a cryopreserved human brain. So I just want to start off making a couple of comments about the relationship between cryonics and science. So there's this syllogism that's of significance now in the way cryobiologists view cryonics, and it goes like this. Science is a method for discovering truth. Cryonics is an act of speculation. Speculation is not the discovery of truth, and therefore cryonics is not science. And the reason that I bring this up is that, thanks in part to some ruckus that was raised at the 1981 meeting of a certain cryobiological society, the society instituted a policy statement about cryonics, and it reads in part as follows. Preferences regarding disposition of the dead are clearly a matter of personal choice and therefore inappropriate subjects of society policy. The society does, however, maintain that, does take the position that cadaver freezing is not science. The act of freezing a dead body and storing it indefinitely on the chance that some future generations may restore it to life is an act of faith, not science. So there were some changes in leadership in the society recently, and as part of the result of that, the statement was updated in 2018. And it now reads a little bit better, and it goes like this. Preferences regarding the disposition of post-mortem human bodies or brains are clearly a matter of personal choice, therefore inappropriate subjects of society policy. The society does, however, take the position that the act of preserving a body, head, or brain after clinical death and storing it indefinitely on the chance that some future generations may restore it to life is an act of speculation or hope, not science, and as such is outside the purview of the society. Now that last line about being outside the purview of the society, that's at least a little bit of an improvement because these policy statements have underlain the expulsion of cryonicists from membership in the society and inhibition of discussion between proponents and opponents of cryonics, and the existence of cryobiologists who are interested in cryonics as basically lepers within the society. So we'd like to sort of examine how these issues could be improved. So let's talk about the issue of the difference between cryonics and science. Science proceeds by constant testing of hypotheses. And cryonics claims to be a scientific experiment. We cryopreserve you now, we wake you up 200 years from now and see if it works or not. That's the experiment. The problem is that it takes decades or hundreds of years to get to the end of that experiment. So for the time being, any scientist looking at this proposition is going to regard this as useless from a scientific point of view. You cannot evaluate this idea because we can't do the experiment now. So in science, Karl Popper in 1934 wrote a book called The Logic of Scientific Discovery. And he put forward the idea that in science, the reason that science is good and works is that in science you can define a good hypothesis versus a bad hypothesis. And a good hypothesis is one that theoretically can be challenged and falsified if it's wrong. Such as a good hypothesis might be all swans are white. And you can challenge that and disprove that hypothesis if you can find a single black swan, for example. you never find a black swan, however, then the hypothesis stands until it's later falsified. So in cryonics, you might say, well, our hypothesis that some cryonics will survive, or there's hope of survival, or something like that. That's a bad hypothesis, because we can't do the experiment now to test it. Because that premise depends upon technology that doesn't exist now, molecular medical nanotechnology, and we don't have that yet. So this hypothesis is worthless from a scientific point of view because you can't test it, you can't falsify it, it's impossible. But there are good hypotheses that can be created within the realm of cryonics that can be constructively used to build the case for cryonics gradually over time, incrementally, such as the hypothesis that Robert McIntyre had some time back, and we tested in our lab at 21st Century Medicine, that aldehyde stabilized cryopreservation can preserve brains well. So that hypothesis was not falsified. That hypothesis was proven to be correct from what we can see. Another one is that human brains can be mostly vitrified, and this was actually taken on by Alcor, but it decided to do CT scanning of their cryo patients and examine and quantify the amount of vitrification that actually takes place in the human brain in real-world cryonics cases. And then you all remember another cryonics hypothesis that was put forward, which is memory can survive after either freezing or vitrification, and that hypothesis was not falsified either. That was upheld by the scientific method. And so these hypotheses kind of began to reconstruct or construct a case for cryonics, starting from one in which no viability is possible, which has questionable validity, in some domains, to in a very practical demonstration, at least we can get to the vitrification part of this process, to a principle establishment that the goal is not intrinsically impossible, because there's at least one example in which memory can survive, opening the possibility that memory could survive in people as well. But we'd still like something a bit more direct if we could get it. So that comes to the hypothesis that I'm going to spend the rest of this talk talking about, which is the hypothesis that cryonics can sometimes preserve human brain structure without major injury from ice or loss of cytoplasm or synaptic connections, because if you don't preserve brain substance and brain structure, it's unlikely that cryonics is going to work. But if you can, it opens the door to cryonics possibly working. So we want to at least establish that much. Unfortunately for us, and unfortunately for one particular individual, Dr. Stephen Coles, we had a chance to test that hypothesis a number of years ago. So Dr. Coles was the leader of a gerontology research group, and he developed a fatal pancreatic cancer and had to be cryopreserved. They had not planned for it in advance, and he had no money available to pay for it. And fortunately, he did have a wonderful wife who supported him, and so he was able to do whatever was necessary to get the process done, provided there was some mechanism to accomplish it. Alcor, on the other hand, played an incredibly significant role here as well, because Alcor consented to do an experiment that would allow Dr. Coles to be cryopreserved without having to pay for it in exchange for investigating that particular hypothesis, as well as a secondary hypothesis. But Dr. Coles had not signed up for cryonics, partly because he regarded fracturing as the equivalent of cremation. He did not think that fracturing injury would be reversible, so he was just skeptical. But the proposition was put to him, Dr. Coles, suppose you become the person that answers that question once and for all. We can design an experiment that will hopefully not fracture your brain, but still allow you to be cryopreserved and stored for geologic time periods. Are you interested? So he said yes. So the secondary hypothesis is that brain fracturing can be prevented by halting cooling at minus 140 degrees Celsius and subsequently storing it indefinitely at that temperature. So here's the proposition. All of the costs of cryopreservation will be covered by Alcor, the Alcor research budget as a charity case. But the conditions are that the brain must be removed so it can be inspected for cracks after vitrification, which is feasible because in research done at 21st Century Medicine on vitrifying whole pigs, we could demonstrate that every time we saw fracture in an organ, it started at the surface of the organ and propagated in. So we didn't have to dice up Dr. Cole's brain into little pieces to look for fractures. All we had to do was look at the surface of the brain and preserve the great majority of the brain to get that done. So the second sacrifice that Dr. Coles had to have, in addition to having his brain removed from its skull so it could be photographed all the way around for cracks, is that it had to be biopsied several times. So we could test for the ice formation tendency of the brain and for the ability of his brain to take up cryoprotective agents. But also, perhaps most critically, so we could look at, for the first time, the structure of a human cryo patient's brain after preparation for cryonics, both at the light microscopic level and at the electron microscopic level, with the ultimate goal of publishing the results in a scientific journal. Now, there's an interesting wrinkle to that last part because Dr. Coles wanted to be a co-author on the paper. So I promised him that would happen. Okay, so here's how this case went. And I have to say that the case did not go perfectly. It went the way cases usually do, with lots of imperfections, questionable events, and problems. And that's good in this case, because that's the kind of situation we want to test. On the other hand, it was not a basket case either. He didn't wait, and get discovered 2 weeks after he died. He was very prudent. He knew he had less time than people were telling him, so he moved to Arizona, checked into a hospice near Alcor, and proceeded to decline over several days. And the manuscript about this will go into great detail about his physical state during those agonal days, and which were not always pleasant or wonderful. But Alcor was able to arrange a standby and transport to Alcor after deanimation. The transport actually was accomplished 1 hour and 24 minutes after arrest, so it's not like he was instantly whisked out of the hospice and into Alcor. It did take some time. And then his cephalon was isolated for perfusion, and that isolation took 1 hour and 8 minutes after he arrived at Alcor. More time passing, more cold ischemia, more chances for things to go wrong. And then the cryoprotectant perfusion was started a total of 3 hours and 16 minutes after cardiac arrest. And that's significant because there was a big cardiovascular surgeon in Madrid that I met at one time who said he was not interested in cryonics as he was sure the human brain could not be reperfused 3 hours after clinical death. And this case actually puts the lie to that hypothesis. In any case, then the brain had to be removed. Ironically, the usual surgeon who's on hand to do procedures for Alcor at the time was not available, so Alcor found somebody at the last minute who had never done a cryonics case before, and this guy actually had to remove Dr. Cole's brain, but he did it successfully. And then the brain had to be sampled using methods that Alcor never tried before, which were conveyed to Alcor by email like 5 minutes before they had to be done. And so everybody was going crazy and feeling very much under pressure and under the gun, but managed to do it correctly right at the last minute, mercifully. And then we had to do a controlled cool to minus 140 and not below. So Hugh had to rig that up at the last minute to make that possible, which he very successfully did. And then we had to do the photography of the vitrified brain to see if it fractured or not. That required more jury rigging at the end there after a fairly short amount of time, but that was accomplished as well. And then the last part is just long-term storage, and that part is underway. So this just shows the time course of the procedure and some of the warts in Alcor's data tracking system. The dark line that you see in the upper right panel is the arterial concentration. You see it's reading lower than the venous concentration, which is impossible. So they had a problem with their refractometers, but you can see that the introduction of cryoprotectant went smoothly and fairly linearly for a while. There was a pause to allow CPA uptake, and then there was a final jump to the final M22 vitrification solution. You can see at the lower left panel that the initial perfusion was done around 3 degrees Celsius or so in the environment of the cephalon, and a little bit colder than that afterwards. And that the perfusion, as you see on the right with the blue line, was done at 130 millimeters of mercury during the early stages of cryoprotection, and then at 100 millimeters of mercury later. So here's the fracturing experiment. So Hugh did a beautiful job of putting this together. There's a nice linear cooling rate here of the environment and the brain surface temperature. There were no internal probes, so we don't know quite what the brain internal temperature was, but I can tell you it probably caught up to this by the end. But unfortunately, despite the beautiful job that Hugh did, he was kind of asleep at the switch when you actually got to minus 140, and he left the brain unattended for a few more hours, and it went down to minus 147. Obviously, the farther you go down in temperature, the larger the risk is that there may be fracturing, so this could have easily messed up the experiment. So when I chastised Hugh, he very gingerly brought the brain back to minus 140, and we all hoped for the best. And the answer was there were no fractures. No fractures. So the reason I'm showing you this image rather than the image of the brain is that the image of the brain was electronically captured and the electronic file was accidentally erased. So that's terrible, but eyewitness accounts are unanimous in saying there were no cracks. And this is the kind of environment that had to be set up because you can spray liquid nitrogen into an environment like this, maintain the temperature around minus 140 without a lot of vapor, so you can actually do the photography without changing the brain temperature long enough to determine the answer to the question and then stow it in this long-term storage container. Okay, so now let's go to the more intense aspects of this test, tissue sampling. So this is a typical example of the surgeon remaining a fairly hefty sized biopsy from Dr. Cole's brain. The biopsies were taken bilaterally and from the top and the bottom aspects of the brain. When I received them, they look kind of like this. They're in milk tubes and they're labeled for either EM or DSC. As you can see, they're all kind of amber colored, which means that there's no visible ice in them. If ice had formed in these things on a macro scale, you would have seen white spots or whiteness. There's no such thing. And so I organized all these things in these 50 milliliter tubes so we could then process them. So you have to figure out how to handle these tissues so that you can preserve their properties faithfully. So in terms of determining how much CPA they had in them and how resistant they were to ice formation, I decided to just take these biopsies, drop them into M22 at room temperature so we could warm them quickly. And then immediately, as soon as they warmed in a few seconds, we blocked them so that the M22 they were dropped into would not penetrate into the tissue and screw up the results. And by doing it this way, there was no frost condensation on the samples, which would have diluted them and given us a false result. So then after you take this biopsy and warm it up, you can cut it in two and use 1/2 of the sample for ice formation tendency, DSC, or for cryoprotective agent content by HPLC. So without belaboring this too much, these are the kind of protocols we looked at. So we wanted to know if Dr. Cole's brain was susceptible to ice formation on slow cooling. So to do this, you do a slow cool, about minus 90, and then you do a fast warm back up to above 0. And if ice is going to form during slow cooling, it will, and then when you warm it up quickly, you're going to see a spike. You're going to see a melting peak. And as you see on the right side, there's no melting peak at all. And so there was no ice formed during cooling. You see this temperature excursion on the left, but that's just the DSC sort of figuring out what to do. That's actually not any sort of freezing event. And then the stringent test is, okay, so there's no ice formed on cooling, but could there be ice? Maybe if there was a slower cooling event, there could have been ice formation on cooling. So let's see what the maximum possible ice content would be in Dr. Cole's brain if it had been subjected to bad conditions during cooling. So it's kind of an elaborate procedure, but basically you cool to minus 120, so it gets nucleated. You warm up to minus 60 to allow those crystals to grow to substantial size. Then you cool back down so you can get a clean record when you warm it, and then you warm it quickly. Then you warm it slowly so that you can, not escape any possible ice formation by outrunning it. And what you see on the right is that there's actually no ice formation even on warming. There's a couple of bumps, but that's, again, just the machine getting its bearings, and you can tell that because there's no melting peak. So we were not able to form ice in Dr. Cole's brain, no matter how hard we tried. That's good. Next challenge is how much of our M22 formula actually got into Dr. Cole's brain cells and into the brain in general. So we determined that the liquid content of Dr. Cole's brain, based on the biopsy samples, was about 55% of its total volume. And of that, you can determine that some of the cryoprotectant components of M22 fully permeated 100% of the concentration in Dr. Cole's brain compared to what they were in the perfusate. A couple of components were about 80% of full strength, and one component was down at the same level as extracellular sugars. But you have to remember that the brain was shrunken, and that means that the protein concentration in those brain cells might have been as high as 29%. So you have to add the protein concentration to the CPA concentration. And when you do that, I think that accounts for why Dr. Cole's brain was so amazingly stable against ice formation. So we have to consider this an experimental test a success as well. But now we come down to the real nitty-gritty. This is really the question we're all the most interested in, and that is the structural preservation of Dr. Cole's brain. So we dropped brain samples into M22 fixative, either at room temperature to speed up the worming process, or at 4 degrees Celsius to avoid deterioration at room temperature while the sample was fixed, and let them fix for a while, then wash them free of CPA. And before worming, they were amber colored, therefore seemed to be devoid of ice, and I stayed that way during worming and fixation. It shows the dilution of the brain samples. In order to look at them, you have to get rid of the M22, reduce it by about 1/3 every so often until we got down to 0% CPA. So what are the results? So this is the first light microscopy ever done on an actual human cryo patient. And what it shows is that all of the structure is still there, at least from what we can see at this level of magnification. But what you're seeing is a lot of white spots. What are those white spots? Those white spots are capillaries. They're normal, they're intact, and there's nothing about them that's really showing much damage. Above the headline, you see a little bit of shrinkage space between the capillary and the brain tissue, but there's no debris in that space. So this is 10x. Let's go to 20x. You can sometimes see damage at higher mags that you don't see at lower mags. But now we see the same pattern over and over and over again. And I could show you a million of these images. These are not the only images that we took. Everywhere you look, over and over and over again, without exception, you see the same thing. There's no ice cavities in the tissue. There's no loss of ground substance. There's no loss of mass. The tissue remains densely stained with the histological stains that we were using at the time. And the capillaries, for the most part, look intact. Now, I'll show you some examples of things that might be questionable in a second, but I don't think they actually are. So that's one example. On the left, you see this thing that looks a little questionable. If this actually works. Yeah, over here, it looks a little bit questionable. I don't think that that's actually damage to the brain itself. Yes, I'll explain in a second. So here's another 40x, and you see a couple more of these questionable spaces. One over here, and one over here. But if you look at this area up here, you can see that. I don't know if you can see that. Oh, yeah, right there. I drawn a line through an area that shows this thin tendril of cells next to a shrunken capillary. And if you were to cut through that, you'd see exactly what you see in those other two areas. And you can see that those areas are overlying a capillary. You can see the capillary wall. I don't believe that's actual brain damage. I think that's just an artifact of the way the sample happened to be cut in that area. So the bottom line is that everything we can see on the light microscope level indicates that all the structure is there. Yes, it's dense, it's compacted. We get shrinkage with M22. But that doesn't mean the structure is gone. The structure is definitely there. So if we have doubts about it, we have to look at the tissue more closely with the electron microscope. So we know what the overall lay of the land is from light microscopy. With electron microscopy, we see the details. The details are the same on the electron microscopic level. The tissue is all there. It's condensed, but the capillaries are intact. The brain tissue is not missing. There are no holes in it. There's various shrinkage spaces, but that's about it. Now there is something weird going on in this sample, and that's this funny-looking thing in the middle here. And that is, I think, Dr. Cole's unique issue there. So Dr. Cole's mentation was perfect when he got cryopreserved. He didn't have any symptoms, but he seems to have had something going on up there that led to this, because I've never seen anything like this in any animal experiment that I've ever done on brain cryoprotection or in any human normal case. So I think that that is an artifact of Dr. Cole's himself. And so once again, if you look around the brain at this low power electron microscope level, you see the same thing over and over again. You see intact capillaries. You see things like, I can find them for you over here. You see some shrunken axons, but they're still perfectly intact. They're just shrunken with little shrinkage space around them, but they're perfectly fine. There's nothing non-inferable about them. And you see the same thing over and over and over again. Maybe a little debris inside the capillaries, but the capillaries are in good shape. For the most part, we don't see a lot of shrinkage spaces around the capillaries, which is actually better than you sometimes see in animal models. So we need to now look at higher power electron microscopy to pull out the details, because the tissue is shrunken, which makes it hard to see the intimate details of the structure to make sure it's all there. So this is high power electron microscopy, and what you see is basically the same thing. And I've actually circled some synapses in this figure so you can see them. Like down here, you can see the postsynaptic density pretty well. And you just see the same thing over again, and you see some shrinkage spaces over here, but there's actually no brain damage associated with that, at least structural damage. This is another example showing these actually really beautifully preserved axoplasm within the myelin sheath here. So we used to worry that cryoprotectant couldn't get through here and protect these things, but it looks like they can get protected anyway. Lots more synapses that seem to be intact. But to really look, you have to look at really high mag to satisfy everybody. So here's an example of really high mag. And again, you can see, I can get the thing to work, postsynaptic density, and if you really look hard over here, you can see hints of even presynaptic neurotransmitter vesicles. So, and it's not like these are only found in 1 or 2 micrographs. You see these all over the place. You see the synaptic clefts. You see shrinkage spaces, which means that the spaces are created by osmosis here, which means that the membranes here surrounding the shrinkage spaces have to be intact so that they can respond osmotically to create those spaces. It means the membranes are intact. So in summary, the first ever evaluation of an actual outboard case showed no detectable fracturing, no ice crystal formation or damage, acceptable preservation of histology, good preservation of ultrastructure, a very likely connectome preservation, and I'd have to add also a lack of fracturing, okay, and then I'd say better structure than I often see with rabbit brains, which have been our gold standard up to this point. So the conclusion is that Cryonics hypotheses can be falsifiable, but the good news is that the present hypothesis was not falsified, it was actually supported, and that goes along with previous Cryonics hypotheses about ASC and human brain vitrification and the survival of memory after vitrification and freezing, which also survived potentially falsifying challenges. So Cryonics is opening itself to scientific scrutiny, at least some of the premises, some of the hypotheses around it. But there's one last issue, and that is that the hypothesis we're testing here, that Cryonics can sometimes preserve human brain structure, needs to be qualified in that one, the case does not prove sometimes. It means it happened once. You have to do it at least one more time to prove the point, but that's a minor bar compared to where we are already. So this is a tremendous advance in the history of the science behind cryonics. but there's more coming. There is a scientific publication in preparation that will describe these results to the scientific community for the first time and hopefully begin to change the scientific debate about cryonics. Thank you. But it will also contain more than just this human case. It will contain some animal data that supports it. And this slide just shows the fundamental problem that we had with this case, which is brain shrinkage. As you can see, the structure of a normal rabbit brain on the left looks quite different than what you see on the right. The structures are distorted. You can still recognize things like nuclei, but they look nothing like they do in normal situations. So we did some experiments to prove that even though the structures are shrunken, they're not obliterated. They're still there. They're just hard to see. The way you do this is by partially washing out the cryoprotective agent. If you wash it all out, then you can get into osmotic damage, as indicated by the black X there. But if you wash it part of the way out, then the brain is rehydrated, the structures are less compact and dense, and more easily visible, and more recognizable to your traditional neurobiologist, therefore more convincing, and you don't get into osmotic damage. So this is what you get when you do that kind of an experiment. This is a rabbit brain that was loaded up with full-strength M22 and diluted out to about half-strength M22, about 5 molar M22. And what you see is beautifully preserved ultrastructure with crisp cell membranes, very crisp synapses, many of which have been circled. And you do see weird things like this, like this over here. There's that right here. You see weird things like this occasionally. But whatever this is, it's shrunken, it's compact, there's no debris in the area. It's not damaged, just shrunken. And you can get even better results going to the next level by using Yuri Pachugin's trick of exposing the brain to sodium dodecyl sulfate before you do the experiment. That opens up the blood-brain barrier. You load this brain with M22, you wash it out to 5 molar, and you get a result so beautiful, it looks like an artist actually drew it for us, with just beautiful preservation of synapses, very clear preservation of presynaptic vesicles, postsynaptic densities, all over the place, wherever you look. And this is another example of the same thing. Again, we saw this all over the place, and up at the top of the screen, covered up by the headline, is this lovely non-myelinated axon looking quite beautiful. Now we do see these little twanged areas over here on the side, in which things are shrunken. But again, we don't really see that so much with human brains. So the human brain is actually better than this. I want to thank Dr. Stephen Coles for making this presentation possible. And I want to thank Natalie Coles, who is here with us today, for making this experiment possible. It would not have been possible without you, Natalie. Thank you so much. And I want to thank Alcor, because Alcor was very brave to enable this experiment. This experiment could have led to terrible results. It could have led to embarrassment. It could have set back cryonics. But it had to be done. Because we're not just doing this for the fun of it. We're doing this because we want it to work. We have to see if it's going to work or not, and the only way to do it is to examine it and look at it with unblinking, eyes. So congratulations to Alcor for being brave enough to enable this to work, for paying for this out of its own research budget. I think this is the best research money Alcor has ever spent, and we'd like to see more of this happen in the future. So I just want to say happy birthday, Alcor. Thanks for everybody for coming, and for any questions or any time for them, I'll be happy to handle them. Thank you.
Thank you, Greg. We have some time for questions. Actually, I have a request about, first of all. Next time we do this, can we please not get the protocol at the last minute? We'll be writing things down on the phone and trying to convey it to the operating room. So,
your point is well taken. But that's another compliment I have to give Alcor, though, for being able to really stretch under very difficult conditions to get this critical experiment done correctly. Everybody, I think, at Alcor needs to be congratulated for their role in this landmark experiment.
Let's keep questions very short, please.
Yeah, great presentation as always, Greg. Fabulous.
Thank you.
I've heard about the fracturing issue all my cryonics career, and people talk about that, but I'm not sure most of us really understand it. What size are we dealing with? And obviously, this is all a protocol that is not at -196. This is intermediate temperature storage. It's not yet quite available. Could you address those two questions?
Sure. So the size of a fracture varies depending upon the conditions under which it's formed. So in organs that we've looked at so far, and that Alcor has looked at in autopsy cases on non-brain structures, fractures can actually cleave an organ all the way in half in the worst case scenario. Usually they cleave the organ part of the way, so you see the fracture on the surface of the organ, but it doesn't penetrate all the way through. In the case of brains, that it may break up the brain into pieces, and that would be a problem because then if the pieces shift, your nano repair technology is going to have to not only match up structures on the two sides of the fracture, but also move the pieces into position to do the healing. But you would really rather avoid fracturing if you can. You're absolutely right. It's not possible for most people right now because Alcor, and in fact, no other climate organization that I know of, although maybe the Europeans are ahead of us on this, has intermediate temperature long-term storage available for most people. But Alcor does actually have a dewar that operates at -140 that has room in it for a few more people, only neuros, but not whole bodies yet. But 21st Century Medicine is actually actively engaged in a design for whole body intermediate temperature storage for the Europeans, I believe. So that may be coming online, at least over there. And depending upon demand, it may become available in the United States. It's merely a matter of economics. It's more expensive to store at higher temperatures because you have to maintain those temperatures by feeding energy in, which boils a little bit more liquid nitrogen, but may double the cost. But I personally would rather pay the extra money and not be fractured because that's just one more obstacle between now and coming back, and that would be best avoided if possible.
Okay, do we know if brain shrinkage is a concern?
We know if what?
Brain shrinkage is a concern.
Well, brain
I guess I was talking about the actual structural question rather than the appearance and people worrying about the shrinking brain.
Yes, exactly. So that's the reason that we did the rabbit experiments to follow up on the Dr. Cole's results. So you can always, people have said, people who advocate xenon as an alternative to cryoprotection, they claim that it's obvious that M22 would just dissolve the brain, therefore there's nothing left, and therefore, all these images that we're showing of shrunken brains are just showing soup, basically. And so in order to overcome that objection, we diluted the CPA down to rehydrate the brain so you could actually see the structure. When you do that, it's obvious all of the structure is still there. And we haven't done a molecular inventory in the brain, but I would wager that all the molecular inventory of the brain is still there. So I don't think that the shrinkage is fatal, let's put it that way. On the other hand, it would be nicer to avoid it if we can. So that's the next wave. And there are complications of doing that in clinical cases because after prolonged cold ischemia, the blood-brain barrier starts to become leaky. And so you can't use specific agents to open it. On the other hand, maybe you don't need them anymore. Maybe you can avoid some of the brain shrinkage as a bonus of some of this other damage that takes place. So we'd like to capture everybody under conditions as good as Dr. Cole's, and then be able to add on to that blood-brain barrier opening technology to avoid brain shrinkage. We're not there yet, but even though we're not there yet, I'm very confident that other people preserved the way Dr. Cole's was preserved will have very well preserved brain structure.
Was this experiment done with a control, e.g. a brain cooled and warmed without cryoprotectant?
Well, that would not be a very good control. If you do that kind of thing, you may see some signs of preservation, especially on the histological level, but if you look at it on the electron microscopic level, it will look terrible. I've done infinite numbers of experiments in which I was trying to freeze brains using every cryoprotectant in the book and every concentration in the book, and you don't want to go that way. That's all I can tell you. The results are not pretty. If you don't want your brain to be reduced to hash, it's much better to be vitrified. Now, having said that, we did do an experiment in which we perfused rabbit brains with 3.72 molar glycerol and froze them and pre-substituted them to see what they looked like before you thaw. Because a lot of the damage that you see may take place during thawing. And what we saw is that the brain was shot through with these veins of ice that seemed to course through it, sort of like a basket weave that seemed to sort of be pushing through it indiscriminately regardless of what sort of brain structures might be there. Looks very nasty on a histological level. But when you look at it by transmission or scanning electron microscopy, you find that the ice spaces have smooth walls. They compress the tissue very neatly and compactly between them, and they have not ripped up the tissue. And that will be part of that paper that we're going to publish as well. So there's hope for people whose brains are frozen also, I would say. But the preference would be to do it well.
You're saying Michio Kaku is wrong that the cells don't blow up, explode from the inside.
Yeah, Michio needs to revise his science a bit there.
So the frozen brains, straight frozen brains are not necessarily hopeless, but probably require something like advanced nanotechnology, medical nanotechnology, of getting in there at cryogenic temperatures and fix them. So yeah, we don't want to give up on those, but obviously not the desirable condition.
So if you wanted to make hypotheses about the revivability of straight frozen brains, you're going to have a much harder time finding a reasonable hypothesis. But you can't rule it out yet either.
So one thing, there's a very quick answer if you know it. What date was Dr. Cole's procedure done? 2014?
I think it was circa 2014 or so. It's ridiculous. It took us a long time to get the samples out of Alcor into 21st century medicine. It took me a long time to get them analyzed. But the beauty of cryonics is that you can afford to wait, so we can do the experiment.
Okay, and finally, please tell us when you signed up, and please take a bow as we give you a huge round of applause.
Well, I cannot publicly discuss the first question because there's still a certain leper tendency in certain circles, and I don't want to completely go outside the rails with my scientific colleagues, particularly because I am an official of a certain state scientific organization which requires a little bit of politeness and decorum. What was the second part of the question? Oh, yeah, well, thank you.
I mean, you trying to go forward.
Thank you.